Well, it's only a 40-minute talk, so it only covers so much. My name is Clements. I am a consulting quantitative engineer with Anaconda. My background is in pricing and trading of interest rate exotics. So I apologize, basically right up front, to the varying backgrounds of the people that are here, whether you're familiar with the math sides of things or with the data sides or interested in this field. Basically, this is sort of a pet project of mine. So working in banks, Python has basically become the standard language. Everybody's using Python inside of banks, but despite this, there's really just a few open source packages available for us, and particularly around pricing and risk management. So a few shout outs basically to the existing libraries. Quantopian, DX Analytics, and OpenGamma. So Quantopian, they're all kind of different. They all focus very much on different things. So Quantopian really focuses on investment strategies and doing time series analysis. Hopefully, a fair amount of you are familiar with their stuff. It's very cool. DX Analytics are the guys that do QuantLib. When you look deeply into it, it's very Monte Carlo simulation based. All the sensitivities to various movements in the market are bump and reprice. So it's pretty straightforward and simple. And then OpenGamma was the company that I worked for before I joined Anaconda. And to my knowledge, it's the first attempt that an open source company has ever tried to do to make money out of creating a package for pricing and risk that truly was at the edge of the leading edge of what banks are using internally. And so the intention, well, first of all, so that was in Java. And so I wouldn't recommend, to be honest, anybody really that wants to get deeply into doing maths to use Java. Again, that's very much my own opinion. We had to build a lot of stuff from scratch. And one of the reasons why Python is so fantastic is that you can, bootstrap off the shoulders of giants and work from all the existing open source packages for doing science. So really, if you don't succeed in the first time, do it again. So basically, I'm trying my best to bring in my free time some sort of cutting edge package to do real pricing and risk that can be adopted both by macro hedge funds to investment banks, et cetera, that typically build stuff in-house. And although the idea of it isn't to be a toy for education, of course it is an entry-level thing that people can use to get kind of, if they're interested in the field and that they learn more, when they show up to interview, et cetera, then they're ready to go. And then finally, because Python deserves all the best. So the structure of this talk, I'm going to begin, because I don't know the background of people, with a quantitative finance crash course. The reason for that is to motivate the importance and develop the core building blocks, which are curves for discounting and forwards. I apologize, as I said, to focusing on this quite a bit. And the reason that I'm doing it, kind of the disclaimer, is that because I do this as a side project, I haven't got a full spread. And what I decided to do was start from the ground up. And so what I have right now is really this kind of core start, and then we can build models on top of that. So it's really at this place now that I got all the cores, then I'm willing to actually talk to people and show it. It was kind of before private. And so I'll give a quick look through the package, just the structure of it, and then at the end I'm going to show a notebook highlighting some of the work that I've done to extend some of the Whoopster stuff inside of SciPy's Interpolate to capture specifically risks that we do in finance. So the basics. Finance basically is really the study of borrowing and lending money, right? In particular, finance, what you study in schools, is about the study of contracts on contingent claims. So a contingent claim means that you're going to get a certain payoff depending upon what happens, events that happen in the future. So this little picture is sort of what I use in teaching a lot, which basically it's showing that these solid lines heading upwards are going to be cash flows that you're receiving, where you know what the payoff's going to be. The ones facing down that are squiggly mean that they're dependent upon some sort of event in the future happening. And then these X's here are options. So basically what you're looking at here is a picture of a swaption, so a Bermudan swaption, where you start getting cash flows that are being traded back and forth, and then you have an option, periodic option, to basically break the contract. So these are basically the fundamentals of the exotic swaps desks, where I used to work. So basically all three of the components that I've shown above here, both the fixed and contingent cash flows and the options, all basically share the same foundation, which is the discount bond. So really what a lot of it boils down to in finance is how do we calculate the value of a dollar at some future time t? So let's go through this. So what banks basically do is lend money, as I mentioned before. So as such, most of the products look like a bond, and in particular, it's going to be some sort of coupon, which basically they pay interest, and so periodically you borrow some money, and then periodically they pay back interest until the principal is paid back. So this form that you see here, where you have like 2 dates, and then one kind of has some sort of sense of you're accruing interest over this period, and then it kind of gets paid in some coupon, is pervasive. So even if you're not in interest rates, because everything's sort of structured on the back of bonds, the same form shows up in FX, credit, even structured equity. A lot of things are built very much to look like this, and the options embedded in some various loan structures look like that. Okay, so what am I saying here? What I really want to say in this part is, I don't know if anybody was here at Alex Samuel's talk. If you weren't, I recommend taking a look at it. What he did is he spent a lot of time focusing on time. And the meaning of time in Python is quite complicated. There's scientific time, there's issues of time zones. He focused a lot on that. There's different libraries within Python to deal with it. Now, finance has its own concept of time. And I've probably rebuilt 3 times, basically different calendars to extend dates. So as we saw here before, we have 4 dates, even in the simple little coupon. TS and TE are the start and the end dates of which interest is actually accruing. And then your F is when whatever event was that makes this kind of payoff determined. And then the TP is when this thing's actually paid. So basically you have this calculation about like, what do you do with, how do you calculate what that value tau is, like how many fractions of a year there is, how do you then adjust for business dates on fixing, what do you do when you land on a weekend or a holiday, like there's a lot of work involved here. Let me see. So yeah, exactly, we try to complicate everything. So as an example, what do I have here? Can I get out of this thing? Why can't I get out of this thing? Let's see if I press a button. Cool. If you do live in this world, this is from my old company, this is probably the most referenced kind of link there is for OpenGamma, because my friend Mark and Rod has gone to a great deal of work to kind of build up all the conventions and write them all down. Sorry, I'm having a problem using my normal key set on here, but basically down here are all the day count conventions. So these are all the various different ways in which different organizations and institutions around the world decide to count how you measure the amount of interest that gets paid in any day's time or over the weekends, etc. And then after that, you've got all the various indices, and this is all the business day conventions. So this is like all the ways you deal with, just very simply, if something lands on a holiday, all these have different rules, and they're very subtle. Every institution, every country gets the right to have their own, to change it, all the things that Alex talked about. What is going on? Okay, this is my baby. He's 6 months old. Thank you. Oh my God, and now it's not even changing. What the hell? Why is my computer frozen on this thing? God. I literally don't know what to do. No, okay, well that's good business. Okay, so I'm going to quickly go through this. Basically, the most basic coupon that we have is the fixed coupon. And most importantly, the value of this is that it literally looks like what's the value of a dollar in the future. The next one is the floating coupon. And the reason I'm going to go through this is it forms the backbone of a lot of the things that we're pricing. I'm going to quickly pass through this. We have a lot of time. So in particular, there's something called the London Interbank Offering Rate. And so this is a polling rate that banks come up with, which gives a sense of like, if we're going to lend money to you for some fixed term, 3 months or 6 months, what is the value that you would lend it at? Now, although all the derivatives are based upon this rate, it actually isn't actually traded, actively at all. So when we start to then build up discounting curves to get a sense of how much money am I going to pay for a dollar at every different dates in the future, we have to come up with some sort of thing based upon something that's not traded. So we do that by basically inferring the prices of things that are actively traded. Where's where I'm going with this? Now, basically, if you have this hedging strategy, which everything works in finance, it's suppose that in order to price this floating coupon, which has this payoff of R, which is this LIBOR rate over whatever we've counted to be the accrual period there. The idea is if I have $1 at TS, then I can invest that dollar, and at the end of the period, I'm going to have 1 plus R times tau, whatever that thing is. So if I have $1 there, and it's going to pay it off there, what I end up with is an extra dollar at the end. So without being able to send this around, just a simple hedging strategy is that at the end of this period, I want to produce RT. I have an extra dollar, so the idea is I sell a bond that's going to produce $1 at the end, and the value of this coupon here is just the value of the coupon bond at the beginning and the value of the coupon at the end. So this is kind of what you'll see in schools. Unfortunately, it's not what we get to do, but this is, of course, the basis. So the idea is that this coupon is just basically the difference of two zero bonds, as was the other one previously. And so when we talk about forward prices, I'm just going to bring this up so we're going. The idea of the forward price is it is an agreement basically to trade an asset in the future for some fixed price now. So we make an agreement for how much this thing is worth such that we would trade it with zero money being paid at the future time. Or currently it comes to zero price. The reason I write this down is because I'm motivating the importance of forwards. So this is the value for a forward contract. This is the forward price. This is whatever we're going to strike it with in the past. And then that's a discount bond for the end. So swaps, as we've kind of seen now, are just these sums of these two coupons. And so far from what we've seen, this is the only asset that's really traded in the market. You can't get access to anything else, even though it's these discount bonds that I need to price anything. So basically, as I said, once we have our core set of assets and we've figured out a curve, we can then price anything we need to. So in the library I've built, you can arbitrarily choose what type of interest rate you're going to use. In this case, I've chosen just one that continuously compounds, which is beyond this talk. The importance of that is such that the derivative of that with respect to the underlying rate is just the time itself, the date itself, times the discount bond itself. So going through this, the reason that gets complicated is that at the top you've got a vanilla swap, which is what I talked about so far. When I showed before, the difference between one floating coupon was just the coupon bond at the beginning minus the coupon bond at the end. When you sum these things up, they all kind of balance each other off. This coupon minus that, that minus that, that minus that. So the value of this entire leg is going to be the coupon bond at the beginning price minus the one at the end. Okay, and so that is true whether it's this one, and it's also true whether it has a different frequency. And so the issue here with pricing is that this is called a basis swap. Basically, you're trading two different things. This could be two different currencies, or it could just be two different frequencies. The point is, given the textbook pricing, if you're only pricing off a single curve, this thing should have zero value. But in the market, it trades with a spread. So that when you actually pay this one side of it, typically this side, you'll have to pay an additional fixed spread. And that's how we price it to zero. So if you want to actually price any derivatives that have a sensitivity to, let's say, 3 months rate, and another one to the 6 month rate, you pretty much have to introduce two different curves. So this is just motivating why this is more complicated than what textbooks are. Let's see. Okay, so jumped a little bit here, but the situation is that we are pricing a bunch of things that have cash flows at arbitrary dates, and we have a set of curves that we want to price, and these curves have kind of nodes on them. So again, in the simplest case, you have a node wherever you're going to need a discount price. But for pricing the value of a portfolio, it has a whole bunch of arbitrary times when it actually is being paid. And so in reality, you're going to have to do a big calibration exercise where you then get the value of those coupons by interpolating. Right? So what we're effectively going to do now is both calculate different curves and also calculate how to interpolate them. So what this really comes down to is a big problem in multidimensional root finding with interpolated values within them. So I get this big Jacobian matrix, which is the value, this is going to be the present value of some sort of asset, divided, the derivative with respect to, in this case, one curve, and then in this case, the other curve. So I'm using one curve to calculate forwards, another curve to calculate discount rates. And so what you're seeing at the top is basically the derivative of the price with respect to the curve itself. In order to do that, I need to basically sum up the value of the derivative with respect to the actual, so I got it backwards. The one on the left is the actual price compared to the value of the price of the contracts. And then on the right, it's the value of the contracts to the actual curve itself, right? So this is the interpolation that comes out. Now, again, I'm kind of wrapping up this little crash course. But the important thing here is that we'd shown before that the value of these forwards has a form that looks like this, where it's basically the difference between the forward rate and some strike, and it's discounted by ends up becoming the numeraire. The value of the option to enter into that forward ends up being this, where I have the max of 0 in that, which means that I have the option to get into it at whatever time I need to make that decision, and it shares the same forward. So it looks like a value on the max of the forward. When we actually calculate these things, we're basically taking, we sum over this thing from a probabilistic perspective of what the distribution is, again, kind of beyond this talk. But the reason I've spent so much time on this, on the library that I have on this particularly, is because regardless of the market that you're in, so far I've been focusing on caplets and swaptions, which are kind of the derivatives of the interest rate world. The same reasoning applies to the equity world, to the FX world, to a great deal the credit world as well. So in an equity, it's the exact same story here, where you're entering into a contract where I pay a certain strike in the future in order to receive the asset. So in an equity, I receive one share of that stock in the future, and that becomes my equity forward. When I walk through it, and I won't go through all these details, and you can generalize this as well for things that pay dividends quite simply. The PV of the forward contract looks the same. So it's the forward minus the strike times this discounting factor. And again, so then we start looking in the same way to the interest rate one. They look the same, and then payoff of the option looks the same as well. So as long as we get that forward and we understand basically how to calculate the value from the swap price and the expected income, we need to have the discount curve properly, and then we can extract to our forward. So now that we have the kernel for pricing. And so once you have that kernel, then you can use a tree or a PDE, well, Monte Carlo with kind of some special pieces, or you can do some sort of derivative over probability distribution, which is kind of what's done in black, in the Black-Scholes, and in models that are kind of SMILE models, if you're kind of familiar with this stuff in interest rate banks. Sorry. And it's the same thing with the FX rate. So basically, when you're looking at FX products, the asset in this case is a 1 unit of the foreign currency. Right? So it's how much do I pay in the current currency to get the foreign currency. And in this case, once again, we share the exact same form. Right? This just says the discount volume of domestic currency. So just to motivate this idea is that once I put this kind of Herculean effort into doing the calibration of this thing for the discount curves, I now have a consistent framework where I can price a portfolio of equity, FX, and interest rate products in different currencies and with different spreads. So as you might imagine, this is kind of what's necessary now. And in particular, those spreads that we were looking at after the financial crisis of 2008 became non-significant. So, sorry, became significant. They used to be kind of in a place where people could just wave their hands and consider them to be zero. We can no longer do that. It's gotten quite expensive. Okay, so that's my crash course in finance. I'm going to move on to a little tour of the package, and then finally a notebook highlighting what I've had to do to overcome this. So, now I'm in this weird, look at that. Sweet, we're in luck. Okay, so the package itself is available on GitHub. I'll send a list. Well, it's just at Clements/Pennies. You should be able to do a search on it. Can we see that thing? Let's see, how should I do it? This way? No. Oh, that's no good. Okay, well, I'll see where we can go. Basically, I have a set of curves, and then I build up on these curves. It's a terrible way to do it. I apologize. The job of any sort of curve is to provide a discount factor. As you start building these things up, I've kind of got two simple examples. One's just a constant, but more importantly, the one that we end up using is a discount curve with nodes. So basically, you have some pieces which has n number of kind of nodes in it, and then you interpolate to get any values beside that. Now, this is all relatively bog standard pieces, except for in here, once you get the form, then you're just basically asking for rates Again, you kind of have it set up in such a way that you can either provide a date or you can provide the time from today in some sort of year fractional sense, which becomes quite useful when you're simulating in time or doing back testing. And then, as I showed before, because we're interpolating things with a specific form, which is continuously discounting, you have this kind of flexibility to do that. Then I get really nice setups for the derivatives around this. Now, view. Presentation. This is a pain. Okay, so things really quite simple, really, and I apologize if you guys can't all see this. That you set up basically a. That's no good. What I've basically done at this point is set up a bunch of assets, what I've needed to do, which is this zero coupon bond that we've been talking about, and then the various bond prices themselves. So an annuity basically is just a fixed payment, a set of them, which becomes, well, the core of swaps and the fixed side. And then so I have, so far, what I've built, and I'm kind of showing what's there and what's not, and I'm quite happy to have anybody work with me on this. So I have a fixed leg and a floating leg, and the real core of what I've been doing here is in the curve calibration pieces. So I won't go through it too deeply, except for that the key to this thing is you're creating a Jacobian. Let me see, this is worth actually going through again. Okay, so this is my one little rant about why Python is awesome. Is that, so what I've done is I've had to like do all the work such that I build up pricing functions for all these various legs. You know, it's coming down to a base of discount factors and then also pseudo discount factors, which is basically a fake discount curve that you're using to project the forward curves, which is kind of the way this is set up. And then, so once I've set up the kind of a Jacobian, which is the derivative of the price with respect to these various rates, all the real hard work is being done by SciPy Optimize. So the really nice thing is that, you know, the real hard work, which we had to do in Java, was actually to build the root finder and build this optimization. Here, it's just coming from scipy.optimize. And so this allows you to put in whatever method that you want, pass in the Jacobian in the values itself, and then just update. So, I mean, this is why writing this in Python has been so much better than writing it in Java. So let's take a look. Okay, so how much time do I have? Anybody know? It is next one 3:05. Okay, cool. So what you're looking at here is Jupyter Lab. So basically, what I said in finance, we use curves all the time. It's basically the main thing we do, and in order to kind of set these things up, we have this Jacobian that we've seen before. So basically, what I care about is calculating the sensitivity to some random part on the curve with respect to the motions in all of the points in the curve. So what I'm going to do is some boilerplate stuff here. As an example, I'm basically just going to have a function which is a sinusoid function, and then plot it. So at this point here, so this is what SciPy is basically doing in order to fit the curve. So not surprisingly, these things do a very good job of actually interpolating the curve, but more interested in finance is what's called the dynamics, right? So it's like, how do things work as they move forward in time? So what I'm doing here is I've set things up in such a way, which I haven't done a particularly good job of explaining, that when you, the PDE that gets solved in order to fit a cubic spline is basically on two assumptions. One, which is the first derivative is smooth through all the points, and the second one is that the second derivative is also continuous through all the points, and then you make adjustment based upon the extrapolation end conditions. So what I've had to do in order to set this thing up, let me just show really what I'm kind of trying to do. So let's say I have some arbitrary point sitting here. I want to know that if any of these curves moves up by like a small fraction, how it's going to affect the value here. So in a cubic spline, for example, you can move any point over here and it's going to have long effects. So if you have a piecewise linear, the whole idea of why we like piecewise linear is because the value in the middle only depends upon these 2 points. So it's quite local. Whereas if you're cubic spline, it's very distributed, right? So the idea is you want to have this nice curve and this nice something that's closely bound. The dynamics make sense without having too much funkiness, right? So this is what we're trying to do is And the way you need to do that is to solve an FDE, saying that right? Solve a PDE, yeah. It's using finite difference. Basically, the way that's done is using root inside of SciPy optimize. And but what I've had to do it is to basically create an additional dimension. So what I'm basically doing is solving a stack of PDEs. So what I'm doing is calculating the derivative of each one of these points to moves in the other point. And then what that allows me to do is then see, so I basically calculate the sensitivity of these guys. And as you might imagine, these, I'm going to show this back. So basically, if I calculate the value, what I have these curves on is every 0.5. So I'm putting my curves at 2, 2.5, et cetera. So if I bump a curve itself, I expect the sensitivity to be identical. So I've multiplied this thing. What's the value of a unit move in the node? You're going to expect to have a unit node back, and then nothing else move. It's just kind of a nice property to make sure that it's a simple case. The same thing is true for another node. However, if you get in the middle, then what you start seeing with these curves is that you get these wave effects, right? So you're going to get close to a half move through the 2 points around the center because I'm bumping this point. But basically, if I move any of these points over here, it's going to have an impact. So if I have a long edge of my yield curve, all these things are going to move themselves. So the important piece of this, if you're kind of following along with that, is that once you have these curves built up, I can then calculate the value and the sensitivity to any one of my any one of the assets in a portfolio to any move across the points. All I basically need to do is calculate this thing once for the n number of curves, and then I can get pricing and delta risk for all the various pieces within that. So kind of my big, I had to get this thing right. I guess really where this talk is going to a large degree is that before I was going to show this to anybody, which I'm kind of proud of it, but now only at this point I can now start plugging models into it. So for anybody that's interested in modern finance, by all means come and talk to me and we'll figure out how to plug in more models. We've done the hard work here, which is to make sure that we can calculate all our forwards and then we can calculate all the discounting factors. From here we can then really look at the expectations, which is the distributions of how these models work. And once you've got that, you've got a core. So I mean, if you look at something like QuantLib or these other packages you can find, all you're going to have for this is like some constant, typically. It'll be like e to the minus RT, like you see in Black-Scholes. Calculate the forward, it's going to be, you know, S times e to the RT. Whereas in this case, you have a rigorous foundation for being able to calibrate to n instruments and then be able to get portfolio pricing and risk on a solid foundation. So what I'm hoping to achieve here is to get started at least, and this is kind of baby steps, in the real world, you know, the open source world, to be able to provide something that is a good representation, realistically, of what investment banks are using and build on a solid footing. That's it, basically. Is there any questions? Go ahead. Not at all. So I've really just focused on the math system. I haven't done any of the data wrangling from the talk that was talking somewhere else. So, I mean, having gone through that, like with the last company I had with Open Gamma, there's a significant amount of work. I mean, if you're lucky enough to be in an IB, you've got systems that are pushing these through, and as you know, that's a very significant piece. The good news is that the Python infrastructure has done a pretty good job of bringing those things in. So the things that we use in finance all the time, the main open source libraries, are things like Pennies, things that you can suck data out of things from. They're not really about pricing, but they are about data wrangling. So all the data science pieces that you're using in all sorts of different industries can be the same ones that can be applied here. That's all. I'm just putting a very small layer on existing pieces so people can play around with this. Anyone else? Okay. Oh, sure. Go ahead. Well, that's exactly what this is, right? So, I mean, these are all about contingent cash flows. So we have two, basically. You have a funding curve, which basically tells you how much fixed value is, $1 in the future. And then you also have, you know, the pseudocode, which basically allows you to build forward rates. And these forward rates, I mean, if they're an HJM, they're kind of like a continuous one over a certain spot, but then these kind of market rates, so you have these 3-month various IBOR rates, which apply through all different currencies. And then, as I showed previously, you can build models for equity that have the same underlying funding curve. And then you also can build up a model inside of that for dealing with complications that come arise, like importantly with like events like income and dividends, et cetera, which kind of like get built in. So they all sort of get wrapped around this. The FX as well. The framework for this allows you to solve curves in 2 different currencies. So for example, you're going to have vanilla curves in both currencies, and you're going to have some sort of a currency basis, which is typically a swap, a floating versus floating in 2 different currencies. So that's set up as well. So in this case, you can price FX instruments as well as interest rates in both of the individual currencies. So was there something else that you had in mind? Oh, I mean, I alluded to that a little bit in the beginning. Like, I've spent far more time than I ever wanted to looking at contracts, et cetera. And so, as I said, there's a fair amount of degree with building schedules up, right? So we talked a little bit about that, and I put a little bit of effort into figuring out how to hack pandas and various these pieces to start providing end dates and beginning dates and building up these schedules. And again, just like we talked about with measuring time, measuring how to dealing with dates that end up on weekends, et cetera. Similarly, there's different rules about whether you start from the back and come forward and whether you have stubs. So far it's relatively vanilla. It doesn't have stub rates, doesn't have a lot of, so many funky things. But coming from a world of structured finance myself, a lot of it's the building blocks further here. Yeah. So please, yeah, jump in and let me know what issues, what do you think is valuable, please. Good? Okay. Thanks for everyone for listening. Appreciate it.